Hey, hi everyone. Welcome to today's session, wherein we will go through the evolution of programming language. Why is it important? So, when you write a code or when you start learning a programming language, uh, there are multiple facets to learn that. The two most important parameters are when you are coding, what is your memory footprint in RAM? So that's the most important aspect. And the second one is how much CPU cycles your code is taking, and is there a way to optimize it? So overall, if you look at the problem statement, it's mostly about you have four resources: CPU, hard disk, RAM, and a network card. You're writing a program. You want to get the work done, but all the CPU cycles and the and the storage on your RAM and the IO that's happening on your network and the IO that's happening on your hard disk, you somehow want to optimize it. Because if I can optimize that, I can get the same unit of work done in lesser amount of time. So my computer or my resource will become much more optimized. I would be able to get the optimal performance by writing very tight code. So with this context in mind, we'll go for a deep dive. My name is Kunal Gautam. I work as a principal architect at one of the man companies having in total 16 plus years of experience. I've spoken at multiple Hadoop, Big Data, and AI conferences around the globe, mostly, namely being Budapest, Korea, US, India, uh, and Southeast Asia. So let's go for a deep dive into the history of programming language. So just like we humans have history, humans have developed programming language. So they have also gone through an evolution over a period of time. And what will happen is as we go through it, you will realize that as the languages became more and more matured, as in like from a low level code to a human understandable language, the compiler of one was written in the previous one. And that's somehow shaping that the challenges of a program was taken of a programming language was taken care in the other one. So that's the beauty of it, or that's what we want to trigger in a thought inside you. So it all began in the early 1940s. You started with machine and assembly languages, and the code was supposed to be written in binary. What it means is you literally had to write the code in 101010, something of this sort. Then it moved to procedural languages in the 1950s, like Fortran. 1917-80 is already when we are looking at a structured language, as in C has already evolved. Now keep in mind, C compiler, maybe when it was written the first time, maybe that was written in assembly language. The first assembler that was written, maybe that was written in 1010 exactly. We'll also see how the code looks like for each of them, because that will also give you a sense of uh, understanding how difficult was it to program before and how seamless it has become now. Because all the modern programming languages, be it your TypeScript or JavaScript or Java for that matter, if you look at the construct, humans can understand it. But if you look at the machine instruction, it was 1010. Humans can't. Like you literally had to take the opcodes machine instruction and say that I have to get my work done. So to take those machine instruction and write that in a piece of paper. And maybe there was a punch card that used to punch into the machine. Crazy days, but that's how it was. All right. So we were at C. You were deallocating memory on your own using calloc and mealloc. Then C++ came in, wherein again the free and delete and the smart pointers were there. Then eventually Python came in, and that was let's say the change, wherein the C code was written, C language was used to write the Python interpreter itself. So first of all, machine language code was used to write the assembler for the assembly language. Assembly language was used to write the interpreter for C. Eventually, the C compiler also became C itself. Python interpreter is written in C. Java, when you write the Java code, the Java compiler, that itself is written in C. So you can see that whatever challenges C was having, most probably those challenges were taken care in the higher level constructs as we move forward. Let's quickly go for a code deep dive so that you can start appreciating this fact. So machine instruction in the early 1940s, you can see here, it's exactly 1000. That's how you are pretty much writing the code. Then The assembly language came in the 1950s, and now you can see here it has this all these opcodes or this machine instruction. They have been converted into something that humans can understand: move, add, swap, uh, and these were the opcodes. So opcode and the byte arrays, or let's say the two registers wherein you want to swap something. Then came the high procedure languages like Fortran, which was using again higher level human construct like do, sum, blah blah blah. And now the interesting part, that C came in. So by the time C was there, all your looping constructs, all your relational operator constructs, they have already arrived here. But this was again, there was no classes in C, by the way. You had to allocate and deallocate memory on your own. That's where C++ came in, which came up with the concept of classes. So now you had a class construct wherein you had the instance variable and method as part of the same class. In structure, you cannot have the method. A structure can only have the instance variable. There is no method inside a structure. So C++ somehow encapsulated the instance variables and the methods as a single entity, so that your behavior and the unit value that you want to save, they're all at a single place, making the life of a programmer easy and also the code much more maintainable. Just keep in mind, C++ also suffered the same problem of doing the allocating and deallocating memory, which was part of the programmer's responsibility. But C++ also came out with smart pointers using the boost library, if I remember correctly. And then you simply had to do like creation of an object, the constructor and the deconstructor of the constructor and the destructor, sorry, of the smart pointers used to allocate and deallocate memory automatically. The major change came in when in the early 1990s, your Python came in. So now what Python said was, look, you have to write a code in Python. I will come up with a Python interpreter, which is written in C. It will consume that Python file and allocate, deallocate memory for you. Secondly, you don't even have to mention the data type. It's dynamic typing. So it means that you don't have to say something like int C is equal to 10. You can say C equals to 10. It will automatically figure out that this is an integral number. And in Python, everything is class. Yeah, until unless you specify that it's like a primitive data type like int. Otherwise, everything is integer, integer. What I want to denote from small letter and caps, big one is an object, other is like you are storing it. Just keep in mind, Python had its own virtual machine. So Python was the one who came out with the virtual machine concept. We will briefly touch the virtual machine concept in the little later part of this discussion when we'll go for the OS. But for the moment, just imagine C++ was natively working as the OS was working. Python came out with the concept of a virtual machine. So now you're coding against the virtual machine. And the virtual machine will take care of allocating and deallocating of your memory. And very important one is it's typeless, or let's say it's dynamic in nature. It's not typeless internally. It figures out the type based on the code that you have written. You don't have to define that explicitly. Now came the modern programming languages, wherein Java was there, C++, Java, rest of the stuff were there. And again here, the JVM became even more involved. And they started talking about like, hey, this is a very high level construct. You can write the code against the JVM, you compile once, and that code can be executed across any machine. There's a slight difference, the Python JVM versus the Java JVM. Java JVM is truly machine independent. Python JVM is, when I say the Java JVM is machine independent, that's a wrong statement, sorry. Java JVM is not machine independent, it's machine dependent. The Java bytecode that the compiler creates, that's completely machine independent because it's written against the JVM only, which is not the case with Python. Python interpreter is not is machine dependent, but the Python bytecode that is generated, that is also machine dependent in certain way, because it can work with a very specific version of Python uh, when it was compiled or interpreted. So that's the reason the Python JVM and the Java JVM, they are not exactly the same. Secondly, Java JVM provides a fixed memory allocation. Example, you say that Java JVM minus XMX and XMS 10 GB to 20 GB. It means that, or let's say both the values are 20 GB. It means that the JVM will be allocated 20 GB of RAM. All right. Python JVM doesn't behave like that. Python JVM is dynamic in nature. As and when you're allocating, it can go ahead and allocate the whole RAM or it will decrease. So this is also another major difference between your Python JVM and the Java JVM. Now, a very important facet, again, the same idea, who perceives any processes, like the way the programmer perceives the process versus the way OS perceives the process. It's very different. So first of all, as we understand, like as a human being, we can not touch our organs. We cannot control at what rate our heart is beating. We cannot control when our lungs is working. Why? Because God has not given us the ability to control the internal organs. So you can get your work done, but you cannot control things internally. Similarly, as a programmer, you are allowed to use the resources of the computer, but you cannot touch any of them. As in, like you cannot call their APIs automatically. You have to go through the operating system. It means that you write a Python code or a Java code, or you execute a Python code, Java code, or a VLC player, or you open up a browser. It is all interacting with the OS, and the OS is interacting with the internal hardware and getting the work done. Be it rendering, be it doing your IO from the network card, or be it doing an IO from your hard disk. That's all taken care by the OS, and the programming language is just interacting with the OS internally. It's never touching the hard disk, or it's never touching the RAM, or it's never touching the network card at all. Because that's the distinction, that's the safety OS guarantees. That you speak to me, I'll speak to the hardware. So from the OS perspective, OS creates this specific view for any process. So you have a stack section, heap section, data section, program section, right? But again, just keep in mind, this is the OS view. A program may or might not look at its process manifestation in the same view. We'll get to that, but let's quickly look at what's happening here. So what the OS says is you run any process on me. I don't care it's a Java process, Python process, a shell process, a .NET process, a Erlang process, a Perl process. I don't care about that. Whenever I will create a process, I will create the process having this four section. And what are those? So first of all, let's look at the text section. Text section is the one. Sorry, the text section is the one here, this part, or it's mentioned as program section here, wherein your actual code will be pulled in. All your variables and rest of the stuff will be here. Stack section is the one wherein if you call functions or you call the instance variables, sorry, you call the functions, the function will all be allocated on the stack. Yeah, which includes the function return parameters, function address, and the local variables. It's all part of the stack. Data section is where if you have any global variables or your static variable, it will all be part of the data section. Pretty much, it's like a shared one across the whole program that comes here. And heap section is the one which you have to allocate and deallocate. So in C world, you were using mealloc or calloc, and then you had to deallocate it using the free pointer. So again, a computer or the operating system will always have this specific view where it will create a program. But now the interesting part, you have your laptop. Let's imagine your laptop is having only one CPU. And you have multiple applications running. You have Excel running, you have a browser running, you have a PyCharm running. How is it possible that first of all of them are running? Because all of them are long running process. You start a browser, the browser is continuously running, right? You start a PyCharm, the PyCharm is continuously running. You start a VLC player, the VLC player is continuously running. So how is that with a single CPU? I get a perception as if everything is interactive. I'm able to interact with all of them and all of them respond back. But the challenge is you have a single CPU. So at any point in time, a CPU can execute only one program. So how, as a human being, we are getting a perception that I am able to interact with all of them and all of them are working in tandem? So what happens is, this is the most interesting part here, that as and when you keep clicking on your, for the folks who are coming from the Windows background, you keep opening up different softwares. What's happening is internally inside the OS, it's scheduling that process at a very high speed. But just keep in mind, because it's a single CPU, at one point in time, this one CPU can execute instruction from only one program. And that's the scheduler of the OS. When we will move to the session wherein we'll go for a deep dive into Linux command, you will be able to appreciate that there are commands to even look at where in this state my process is. Just keep in mind, it will happen at such a fast pace that the values will keep changing like at a very high speed. So from the OS perspective, what OS is doing is, as and when you are clicking more and more processes to come in, it's taking one process, giving it some CPU cycles, then evicting it out. Then taking the second process, again giving it certain CPU cycles, then evicting it out. And it's doing that at a very fast pace. Example, a normal CPU that you have nowadays is like 3.2, 3.8 gigahertz per second. It means that 3 into 10 to the power 9 instruction it can execute per second, although at any given point in time, only it's serving one process at a time. But because in 1 second it is able to flip, or it's able to context switch from one process to the other, like it takes the one process from your hard disk, pushes that onto the RAM, uh, get some CPU cycles, and then it gets it out from there, gets the second processor inside my RAM, and then it starts executing the second process. Now, this is happening at such a fast pace that we feel that all of them are alive and all of them are having CPU cycle. In reality, it's not the case. And whatever I have said, it's in the context of a single CPU. All right. So the other diagram shows that how this context switching is happening, or interrupts, what we call, that you have a program control block 0, like pertaining to, this is a data structure that corresponds to one program. And what is the data structure? This data structure is keeping a track of this part. How much RAM program has been taken, how much stack has been taken, how much heap has been taken, blah, blah, blah. Just keep in mind, stack is always a first in, last in, first out. Sorry, stack is a first in FIFO, right? Heap just grows up, stack is growing down. Heap is like you allocate heap and it can be randomly allocated anywhere. It doesn't need to have the stack idea. So stack can only grow one after the time. So when you deallocate the stack, so it starts from the bottom, goes up to the top. When you deallocate, it will just go one step at a time. Pretty much like the stack data structure. Heap is random. If you have 4 GB of heap, I can allocate memory anywhere inside that heap. There is no limitation or constraint saying that no, for the first memory, then only the second memory will pop up. Nothing of that sort is there. All right. So now let's look at the code and also the memory mapping of it, so that you'll be able to appreciate what happened between C, C++, Java, and Python. What really changed? So let's look at, in the C world, first of all, as I mentioned, there is no classes. There was only structure. Structure can only have instance variable. And whenever you wanted to allocate memory, look at this statement, int star arr is equal to mealloc of this. That's how you are able to allocate heap, right? When the program is done, it is your responsibility to free that arr. Yep. But the beauty of this was, as a C programmer, if I understand the OS view of memory, this part, it is the same view that the programmer also has to understand, because C was mapping directly onto the OS. There was no layer in between. And that's the reason, if you understand OS, if you understand how this memory works, then you can write a very super optimized code in C, because you realize that this int n equal to 5, that will go to the stack area. If there was a global variable here, example, before even the int main, sorry, after the int main, let's say at the top level, there was the instance variable that would be stored in the data section. Yeah, this int main is being called, this function is being called. Again, the function will be called where? In the stack part of it. This mealloc will allocate memory where? It will allocate memory in the heap section part of it. So every line in this program, you can map it to which section of my uh, memory, or sorry, which section of my operating system view of the process I am pointing to, and how can I optimize it. So that was the beauty of C, that you can directly correlate even as a programmer, and you can write super tight code here. The only challenge was if you by mistake forgot to free it, or by mistake you started accessing a pointer which you haven't allocated, your program will crash. Very difficult to debug, but that's how it was. Next, come to the C++ programming. C++ instead of mealloc and calloc, they came out with new and delete. So this is like creating a class and then deleting a class. But again, C++ also had smart pointers, and the smart pointers allowed that you don't even have to write new and delete here. Again, the C++ memory view of the OS is the same that is a programmer. So if you understand how a OS keeps a track of the memory for a process, you can apply the same logic there. Now comes the Java virtual machine. So here was the catch. Java virtual machine said that, hey, OS has a view of whatever stack, heap, blah, blah, blah. You don't worry about it. Because what I will do is I will create a JVM. And it's known as Java virtual machine. Instead of a real computer, it's a virtual computer. What you have to do is you just have to look at the instructions that I will provide as a JVM, and you have to code against me, not the OS view, memory view of a process. And I will be interacting with the OS. So what JVM said was, first of all, JVM has a capacity that you have to define beforehand. So when the JVM starts, you have to say XMS and XMX. XMS means that what is the minimum value of the JVM that it can occupy on the RAM, and XMX means that what is the maximum value of the JVM it can grow. And I can also give the XMX and XMS value as the same. Example, I have a 20 gigs of RAM. I can say my Java JVM minus XMS and XMX is equal to 4 GB. It means that JVM will only occupy the 4 GB of my RAM. Just keep in mind the JVM process itself always will have the stack area, heap area, blah, blah, blah. But as a programmer, I am not worried about the OS view now. I'm just worried about the JVM view. What JVM says that go to documentation, see how I'm asking you to allocate and deallocate memory. You just leverage those APIs. You don't worry about what I internally do with the OS. Which part I will map it to the stack, heap, blah, blah, blah. You don't have to worry about it. That's my problem. And because you are coding against the JVM, it made it truly machine independent. So the JVM process, it's a C code. So that was machine dependent. But what was happening is you took the Java code, you compiled it. So there was a class file which you used to get. And the class file was getting consumed by the JVM to get the process done, to get the work done. And this byte class or the Java byte class, it's pure, truly machine independent. So you can compile in one machine, Mac. I can take the same byte class. I can go and execute that on a Linux machine. Completely doable. And then came the Python. Again, Python was very much similar to Java. You don't have to worry about garbage collection. You never did a new anywhere. You didn't even define the data types. So Java is strongly data type. You see here, you are defining int n is equal to 5. So it means that 5 is an integer, n is of data type n. Map it. But you see here, you are saying n is equal to 5. There is no data type. Because at runtime, dynamically it will figure out, hey, this 5 is an integral. So Python was giving you that benefit. Secondly, Python also runs on the same idea of virtual machine. But just keep in mind, its virtual machine is not having a min and max. It can pretty much go and consume whole of RAM. Right? Secondly, when you interpret or compile the Python code, it also generates a bytecode. Yep, but that bytecode is not in reality machine independent. It has dependency on the machine. Secondly, it has a very strong dependency on the Python compiler version. So for example, I take a Python program here, I compile it, I take it to a Linux box, and let's say if the Python interpreter are not matching, it will fail. Yep. So that was the difference between the Python virtual machine and Java virtual machine, and the journey of how the memory footprint is happening everywhere. So again, in context of Python, just keep in mind typeless or dynamic type. The Python virtual machine is not constrained. It can occupy the whole of RAM if required. Thirdly, the Python virtual machine consumes the Python byte array or the Python bytecode. That Python bytecode is not truly machine independent. And that's the reason Python was never called a truly machine independent program. Because the machine independency was from the bytecode perspective, not the code perspective. So it was like you compile once and you execute multiple times. This is what is meant by machine independent. Again, re-emphasizing, neither the Python virtual machine, neither the Java virtual machine is machine independent because they are written in C. Only the bytecode generated after the compilation in Java or the interpretation in Python. This is what we are comparing. That can that be a machine independent or not? So Python is not, Java is. Great, folks. So, folks, I think this would have given you a very good insight around how the evolution of the programming language happened and how the memory mapping is there, and how, as a programmer, you should be looking at the memory layout of your code to write super and tight optimized code, both in terms of CPU, RAM, hard disk, and network card. It was great preparing this presentation and looking forward to meet you all for the next steps. Thank you.